Hi. I love doing this because I've been doing HPC for 53 years. And so I really love to encourage people like yourselves to make it a career because I'll tell you, it's been phenomenal. It's really been great. A lot of satisfaction in making codes run faster. And it's good, hard work that's rewarding. So today I'm going to talk to you about taking an application. The name of the application is Leslie 3D. It's a three-dimensional computation fluid dynamics code written in Fortran. I only do Fortran, by the way. So I know two languages, Fortran and English. All right, I'm going to be using 4 to 8 Intel Broadwell nodes. Each of those have 44 cores per node. I have been running on Theta on the KNLs, so all this works on the KNLs fine. I'm using a little bit earlier Perftools, but it looks like everything works fine with the version that you have on Theta. I also have some GPU statistics and work, and I was using P100s, 4 nodes with P100s, and then I ran scaling runs on PISDANT in Lugano, Switzerland, which is where I'm going to retire. Beautiful place. Okay, so Cray has made it extremely easy to use these tools. They've come up with a Perftools-lite suite. There are 3 major versions: Perftools-lite, Perftools-lite loops that gets instrumentation of the do loops, and Perftools-lite HBM, which gives you memory analysis, which is totally awesome. And so all you have to do is load one of these modules, only one at a time, build the application, run the application, and the statistics report comes out with standard out. We do have fancy displays and like that, but I just like text. I guess it just shows my age. It also generates a directory that you can do further analysis with. So this is Perftools-lite profile run on 8 nodes where I only use 1 MPI node per MPI task per node. And it's your typical profile. Now the sampling is 1/100th of a second. So this thing ran 40 seconds. And so you can see that there are, like 6 or 7 important routines. Now this is only showing you routines that use more than 1% of the time. If you want them all, you can override it with a -T on the PAT report, which I'll show you. Also gives you imbalance. This is extremely important when you're running large numbers of MPI tasks. You can narrow down to which MPI tasks are causing the imbalance. Then table 2, that was table 1. Table 2 actually gives you the line number within the routine that is used. That one line number is using 14% of the time. Okay, so if I go into the code, I see that it's a call to Visc or to Visc J. Now these things, one of the things when you compile with the Cray compiler, you want to use -h list equal a, not minus a. That's a mistake. And F means that all the calls within that loop have been flattened. In other words, they've been inlined. A V means that there's a loop down in there that has been vectorized. This has all been vectorized. A D means that that was not executed, it was deleted. And we'll get into some other stuff. All right? The actual line number is right there. Now this comes out in the routine name.lst, your listing file. Now whenever you see a plus, it means that additional information is available at the end of this routine. And that additional information basically says a loop starting, in other words, this is actually down in that subroutine, requires 25 vector registers, and 2 of these have preemptively been forced to memory. So this is really important for your cache utilization, L1 cache. So it's really good stuff. All right, now, if you now do a pat report with -OCT on the statistics directory that Perftools-lite produced, you get a call tree. So the call tree starts with less 3D, and then 27.8% is spent in flux K. 19.9% of that is in flux K, excluding all the routines that it calls. 7.9% is spent in extra PK. Okay, so you get a really good idea. You come down, you can see where the MPI is. Flux I, parallel is actually called from les 3D, and that calls MPI CX, which calls MPI send and MPI CX exclusive. So this is the nesting level of the call tree. You'll see where this is extremely important when we go to GPUs. All right, the next thing I want to show you, totally different run. I have to unload Perftools-lite, and I have to load Perftools-lite loops. Perftools-lite loops now gives me a profile of the loops that use most of the computational time. It also gives me the number of times the loop was encountered and the min, max, and average iteration count of those loops. And you can see that a couple things from here. You can see that these two are tightly nested because those two loops are one right after another. But you can, these 3 loops that are basically red are kind of our major loops in the program. And then there's some other ones that we'll get to later. But the display that really kind of, so I said all that. So how do I find out really what the most important loops are? Well, what I'm going to do is I'm going to do a pat report -o call tree on that statistics file generated by Perftools-lite loops. All right, now, this is, you're supposed to say, oh my God, that's wonderful. So here we have a loop, very important loop that's actually using 11.4%. It's doubly nested. It calls Levesque. Now then, it comes back into flux I, and it calls extra PI, which has a double nested loop in it. All right, and then, so you see you have a structure for flux I that's very similar to the structure for flux K, that's very similar to the structure for flux J. They're just 3 sweeps through the grid. All right. So these are the first 3 loops that we really want to attack. Now, what are we going to do? We're going to use OpenMP on these loops. Now, these loops call subroutines down the call chain. This is a very difficult problem for scoping variables on high-level loops. But we want to help you do it. Okay. So, we have a package called reveal. Now, let me tell you that right now, reveal does not work well with C++. All right? It works very well with C and Fortran. We're trying, I mean, C++ is just terrible. I mean, because when you look at this from a compiler standpoint, you have no idea what the addresses of all these arrays are. So how can you do dependency analysis on a high-level loop in C++? It takes a lot of user interaction. And we are trying to work on that and improve reveal. But right now, how many of you have Fortran codes? All right. Yes. I'm not even going to talk to you C++ people. All right. So there are 2 things that we need for reveal. And I think I missed saying this. The first thing we need is a program library. Now, what this is going to do is it is going to build a program library of your entire program. Now, this might take a little while. It might use a little bit of disk space, but it's very helpful. So you need that. Now, very important, when you build this library, you don't want any of the Perftools stuff loaded. All right, you just, unload that. And then what happens is you give Perftools the library and the statistics directory that has this call chain, call tree. And what comes up here is a list of all of the loops in order of how important they are. Now, reveal tries to do a really stupid thing. It does an initial analysis and it says, wow, we should analyze that loop. So it puts a gold star on it. Now, this outer loop is the time step loop. We're not going to parallelize that. So basically what we're going to do is we're going to go to this flux I loop, which is right here. And so we're going to look at that. All right? And so we click on it, and it comes up over here in the window. And then we're going to right-click on that. Well, first off, you also get all this listing stuff, and you also get diagnostics down here. But what I'm going to do is right-click on this loop, and it's going to say scope. And so I'm going to click on scope. Right. A scoping window comes up. How many of you have used OpenMP and had to scope variables in a loop, private and shared? Is it really easy? No. So we've selected one loop, so we click to start scoping. This invokes the compiler. The compiler looks at that loop and it says, oh, you know, I can't automatically parallelize this thing, but I'm going to tell the user why I can't. So there are 5 variables that the compiler is confused about. And so now it takes a knowledge of the application. Many of these variables are what I call array constants. In other words, each pass through the parallel loop, an array value is set and then used. Now, in order to not have a race condition, all of the elements that are used must be in the set of all of the sets. In other words, there must be a set each time through the loop of each variable that is used in that array. And this is something that's very confusing for the compiler. Now, what the compiler does do is it scopes either variables as private, shared, conflict. Conflict means that, hey, there's really a recursion here. You know, you're going to have problems. And the other thing is unresolved. I don't know what to do with this. Okay. So what I'm now going to do is go over a few scoping rules. Now, you all probably know these down pat, but the whole idea is that you have to scope things as private or shared. There's nothing else in a parallel loop. And the thing that really gets you are these array constants and array constant reduction. For example, if I'm parallelizing on K, A of ij is an array constant. because it's independent of k. So what I'm going to do is I'm going to select one of those variables, and we go back to the other window, and it highlights FSI. And notice that I comma 5 is set, I comma 7 is set, I comma L is set, and then it's passed down to viscous. And in viscous, it's used from 1 to n spec I. So the compiler just doesn't have the smarts of determining if all of the uses are covered by sets. So I look at this and I said, hey, dude, we're okay here. And another one was QS, and it's a similar kind of thing on QS. And then there's some other crazy scalar things that I submitted as bugs because the compiler should have done it. But just here's a few simple rules. If a scalar is set prior to being used each time through the loop, then it's private. All elements of an array constant must be set prior to being used each pass through the loop. In those cases where not all the elements of the array are set, you might have to do first value getting. In other words, the master gives all the threads the first value of the array. Okay? All arrays dependent upon the loop being parallelized should be shared. And reduction functions are special cases that must be in a reduction clause. And any variable that is just read is shared. Now, you know, it's funny because in the old days, we ran into this and we said, oh, common blocks are terrible because if you have a private variable in a common block, how can it be shared or each thread have their own copy? And then we thought, well, hey, modules are going to fix that? No. Modules didn't fix that. So basically, if you have a private variable that's in a module, it has to be on a thread private directive in the module. Okay. Now, there's this whole idea of last value getting or saving and first value getting. Last value saving, and believe me, very small percentage of times have I ever in my 53 years seen someone use an array constant outside of a parallel loop. So last value setting or saving is very expensive because you have to have the last thread save that value to the master, the thread that does the last iteration. What if there's a decision process? It's very expensive. First value getting is not expensive, and I've seen that quite a bit. In fact, that's usually where I make my mistakes. Okay. All right, so basically what I do is in that other window, I guess I don't show you again. But in this window, I can right-click on this and change unresolved to private or shared. Now, when you do that, you might make a mistake. So don't blame reveal. Okay. So basically what we did is we went in and did resolved all of those unresolved and reveal sticks in the OpenMP directives. And then upon exiting, reveal asks you if you want to save that file. All right, so here is one of those results. And now notice M stands that basically says this is a multi-threading region. And then little m means that the work is distributed across the threads. So if you just have a parallel somewhere up there, you're going to get a big M. And then, of course, this is flattened and vectorized. Okay? All right. One thing, reveal does not use default, which is really pretty good because it really shows you that it did do analysis on these variables and they're okay. All right. So now we run that with Perftools-lite. And lo and behold, we're running 29 times faster on 44 threads. Am I cheating? You know, there's so many GPU people that do this. You know, they run on the GPU and they compare it to one processor on the host. Well, we're not going to cheat. So we are faster. However, this one is only doing one MPI task per node, no OpenMP. So let's run with 44 MPI tasks on the node. All right, so we're still a little bit faster, but this sped up a great deal. But look at this. This is the kind of thing you really want to do when you use OpenMP. Compare it to the MPI on a routine by routine basis. Now, this FluxJ loop is running twice as fast with MPI than it is with OpenMP. Any ideas why? Every machine in the future will be NUMA. Over there, we're running one MPI task in 44 threads across 2 sockets. So, Perftools-lite has a very nice display. Table 3 is showing you a set of threads, and it's showing you local memory traffic on the socket the thread is on, and remote memory traffic on the socket that it's not on. So these are pretty good. In fact, we're getting 20% of the memory bandwidth there. But these threads that are on the other socket are horrible. Most of the memory fetches are on the socket it is not on. The reason for this is when you initialize variables in a non-parallel loop, they are going to be stored on the memory closest to the processor initializing it. So, the threads on socket 0 have great memory bandwidth. The threads on socket 1 have bad memory bandwidth. So how do we fix it? Oh, by the way, here's the MPI. MPI forces you, each MPI task is initializing its data, and its data is going to be on the memory closest to it. So MPI solves the problem. That's why it's so difficult to beat MPI, all MPI, with an OpenMP code. All right, so how are we going to fix this? All right. So, I usually do this. I always say something that's on the next slide. So what we're going to do is, this is the way we ran the app run. This is the way we ran the MPI. Now this is saying I want 2 MPI tasks with 22 threads on each socket. So this says I want 1 MPI task per socket. So there's an MPI task on socket 0 and 1 on socket 1. Better. Still not exact, because MPI is just doing everything right, and OpenMP really has overhead. All right. Now, by the way, I did all of these with OpenMP. I didn't show you that, but I used Reveal to do all those. So, okay. Now, okay, so here we have a pretty good OpenMP program. But we haven't looked at memory utilization. So we have a tool called Perftools-lite HBM. This actually instruments cache overflow on the last level cache. And so basically what it's saying, which arrays are responsible for most of the bandwidth utilization. Because if they're hitting cache conflicts, they're going to require more bandwidth from memory. So, FluxJ is using 23.5% of the memory bandwidth. And this is actually some of the counters, but this is the resource stalls. Now, what we're saying here is, in most programs, stalls are due to memory accesses. So this is saying that line 36 in FluxJ is responsible for 4.2% of the memory bandwidth. And line 72 is 7.8, and 81 is 8%. I mean, that's almost 20% of the bandwidth. All right, so let's look at the code. I absolutely hate array syntax. Array syntax was put in the language for the connection machine. How many of you are running on a connection machine right now?
I have one in my basement.
Oh, do you? So, compilers cannot optimize array syntax very well, especially on GPUs. If you have a GPU code using OpenMP offload, never, ever, ever use array syntax. You have to convert it to loops. And that's what this is telling you. This is using a lot of time, or memory bandwidth. This is using a lot of memory bandwidth. Now, this is saying that little f says that this was fused with that. But the compiler's trying to do good, but it just can't do as good as the do loop. So I just took all the array syntax out and put in nice, clean, Fortran loops. All right. Another thing, the Cray compiler tries to be too smart, and it screws up. If you ever see on one of these listings that the Cray compiler is blocking a loop, tell it not to block. I haven't even found an example where their blocking runs faster than, this. As a matter of fact, when I turned off the blocking, it's unrolling loops. That's what the R stands for. All right, so I did that in all the routines, and now it runs 5% faster. This is the rewritten in loops, and that is the array syntax. Okay, let's add OpenMP directives. It is so simple that it's ridiculous. Okay, now, unfortunately, you can't do this week. If you want an account on one of our external machines to use this, it's called swan.cray.com. Send me an email, levesque@cray.com, and I'll authorize an account. But unfortunately, Argonne doesn't have a GPU, a Cray GPU machine.
Yet.
Oh, yet. Frontier will have all this on it, but Summit does not. Okay.
Well,
So,
technically Cooley is a Cray machine, isn't it? But it's not running a Cray environment, and I know that's what you mean.
yeah. So, all we have to do is change that to OMP target teams distribute and just put the private on. Forget about data motion for the time being. Okay? So we do that. All right. Remember, Reveal helped us with that, so we're just using Reveal stuff. All right, now, the capital G is a GPU kernel. The little g says that this is spread. Yeah, look, I put the array syntax back in. That is not right because this is a kernel all by itself, and I want it to be included with the other stuff. But anyways, then after the routine, it tells me all of the arrays that it had to copy to the accelerator and back to get the right answers. So it does all my work for me. Now, we do have a Perftools-lite GPU, but it's terrible. So you have to use Perftools to get GPU statistics. And when you use Perftools, you have to do a pat build -u if you use MPI -g MPI. Run the executable and then do a pat report on the statistics directory. And here's the profile from our first cut, where all we did was put in those target directives. It's running twice as slow, and all the time is spent in copies. Finally, down here, we have a kernel. You'll see that it's waiting for the kernel to finish. All right? So what I did is I converted all of the OpenMP to RFlow target directives. Now what I need to do is take care of data movement. Now, if I go, I'm going the wrong way. So I want to introduce a target data directive outside of the time step loop. All right? And where is that? Well, it's right here. This call chain is beautiful because it pretty much tells you where you should stick the data for the GPU. And so I do a target data map, and it's going to copy everything over and everything back. I didn't really investigate if it needed to do everything back. All right. However, as soon as I did that, I get the wrong answers. Because there's data on the GPU, there's data on the host. I have to synchronize this stuff. So any of the loops that I did not put target directives on yet, I have to do that. The halo exchanges, I basically update from the device to the host, do the parallel, that's the halo exchange, and then update to the device after that. So now I run it. And so now I'm getting some pretty good kernels up there. I think we're running faster than the host now. But look at this. There's still, those copies are around the halo exchange. So what I have to do is I have to go into parallel and figure out what's going on. So I got this, and what's going on are buffers are being packed up and shipped to on the MPI. All right, so let's put those on the accelerator. So I put those on the accelerator. Now, before MPI send, I have to update from the device to the host. All right. Now, on the receive, we don't have to do anything until the wait. And then on the wait, after the wait, we have to update to the accelerator and unpack on the accelerator. So your MPI, you want to do all the packing and unpacking on the accelerator and only do minimal data transfers, just the halo. All right, so now we're doing pretty good. All of these, we still have, this is the initialization, okay? That's before I get into my GPU region. If I ran that for 1,000 cycles, it would go away. All right. But wait a minute, what is this? This is using 16.4% of the time. It's down in flux J, and if I handled my data right, that shouldn't be there. But the compiler sees that I forgot some arrays. So one of the things we have this environment variable that shows you all the message passing. I'm almost done. And it's saying, look at all this data that you're transferring every time you call flux J. And sure enough, I forgot those 3 arrays. So I put those 3 arrays on my data region out there. And now, this is the copy at the end. But, so this is one of the halo copies. But notice the copies are way down. And so all of these guys are really using all the time the kernels. I haven't done anything to optimize kernels. Nothing at all. All right? Now, very nice capability where you can do GPU direct. In other words, rather than moving those halos to the host and back, you can tell MPI that those halos are coming from the device by using device pointer. This is OpenMP, offload directive. Now on our system, you have to also have an environment variable. Okay? It's much easier to code because you don't do any of the updates at all. All right? So, timings. So this is the original with 64 MPI tasks. This is on 4 nodes. And this is on a GPU node that doesn't have very much. This is our initial port. So we did get a lot of improvement with the OpenMP. This is this is the GPU initial port. So this is the OpenMP stuff. Sorry. And now this is when I raised up the data region up to the main program outside the time step loop. And this is where all the halo exchanges are. And then this is with halo packing on the GPU. So we barely beat this. And the reason is because I haven't done anything on optimizing the kernels. But that is the easy part. Now this is a comparison of using the device pointers. It doesn't really show up much until you get to a large number of nodes. And so that's pretty good. Last thing I want to show you is this Cray ACC debug environment, this really helps you a great deal in debugging a program, because it's going to be doing all this stuff and then stop, and you know exactly where it is. This is 1, 2 does a lot more, and 3 gives you everything plus the kitchen sink. So it gives you the strides, it gives you the lower and upper bounds, it gives you the size and everything. So the kernels are not optimal, and this is left as an exercise for you. Okay, so what have we learned? Perftools is excellent. And Levesque always runs over. Reveal can really help, but don't try to use it with C++. Moving to the GPU is difficult. However, it can be done as steps where it's much more manageable. And GPU direct is the best way to do message passing at scale. There.